Good morning, students. So, in our previous class, we have discussed about the quantization techniques and the pulse code modulation technique. So, on today's class, we will discuss about the different types of pulse code modulation technique. So, first of all, the pulse code modulation scheme in the bell system, that is T1 system. It's included in your syllabus, and it's multiplexing PCM and asynchronous PCM. These are not included in your syllabus, that is multiplexing and PCM. The next part is extension with the PCM, that is differential PCM, adaptive differential PCM, and delta sigma modulation and vocoders. So these are included. This is differential PCM, the adaptive differential PCM, delta sigma modulation techniques are included in our syllabus. So we will discuss first of all the PCM in the Bell system. So in the starting of the 1920s, long distance telephone links used frequency division multiplexing. Initially, there is a frequency division multiplexing techniques were used, which requires more number of the amplifiers, and it's built using the vacuum system. So it's a much complex system. So a cable with a bandwidth, for example, a cable in the bandwidth of 3 megahertz can support in principle 1000 of 3 kilohertz voice channels, but 1000 filters, modulator and demodulators are required. So it's a very costly and uses the old technique, that is a frequency division multiplexing technique. Local exchange communicated by the trunk lines. Each copper pairs carried one voice conversation. Using PCM, multiple connection could be time division multiplexing. So new technique is time division multiplexing. So this is the Bell's T1 carrier system. So this is a 24 channel. There are 24 channels. Okay. So first bit is the framing code, and the last bit is the your signaling bit. So there are 24 channels and 193 bit frames, and each frame has 122 microseconds of time interval. So the key carrier is a member of the group of the carrier system developed by the AT&T and Bell Laboratories for the digital transmission of the multiplex telephone calls using the pulse code modulation and the time division multiplexing axis. The first version of transmission system T1 was introduced in 1962 in the Bell system and could transmit up to 24 telephone calls simultaneously over a single transmission line. Okay, so 24 calls can be made using a single transmission line. So this is the basic block diagram of the T1 carrier system. This is the your rotor. There are 24 channels are there. This is just like a your dial in a old telephone system. So 24 channels, and each channel can be connected to the decoder and the digital processor, and your data can be processed. And the receiver and the reverse of this is using. And then finally, the low pass filter. So the input data of a 30-bit ADC comes from the analog multiplexer. This is the digital processor compares the digital value according to the mu law compounding. Mu law compounding has been used in this T1 carrier system. So again, this dialer, then coder, then the digital processor going to the transmission medium, maybe the copper lines, then digital processor at the receiving end, decoder, and again the this dialer which is passed through the low pass filter, and we get the our desired data. So again, this 24 channels are classified like this: channel 1, channel 2, channel 3, channel 4, channel 5, channel 6, and to the channel 24. Okay. Then this channel 1 and channel 2 is multiple bits. Okay, 8 bits of compromise, and the first bit, last bit is your this framing signaling bit, and first bit is your framing bit. This is in this diagram we show this. So T1 frame, the frame is like this. This is the framing bit. First bit is framing bit, last bit is signaling bit, this eighth bit is signaling bit, and the remaining bits are the information bits. These are the frame of the T1 carrier system. Okay, so T carriers can be multiplexed over a high speed via microwave optical multiplexing by the bits, not octet. T2, then T1 after, then T2, T3, T4. T2 has 96 voices, T2 has 6, and T3 has 4032 voices, and these are the megabits. Data can be transmitted over this speed, 274.176 megabits per second. The customer could buy T1 link or part of the fractional T1. So this is the comparison of the T carrier on North America, and E carrier is mainly used in the Europe. So at the zero level, it is 64 kilobit per second, and both rates are same. And the first level, that is a T1, there are 24 channels in each carrier. There are 32 channels. The channel capacity is 1.544 megabits per second, and it is 2.048 megabits per second. At the second level, 6.312 megabits per second and 68.448 megabits per, and so on. These are the carriers, comparison of the T carrier and the E carrier in the Euro. The next is important topic is delta modulation. So in delta modulation is the most popular alternative to the PCM. Analog signal is approximated by the staircase function. Only a single binary digit is required for each sample. So what was happening in the PCM? In PCM, we require multiple bits to transmit the data. So it requires a large bandwidth. This can be overcome using the delta modulation. In delta modulation, only single bit is represent for the sample. So for example, this is your continuous wave signal, and this is your staircase output. Staircase out. This is analog signal. This is staircase function. Staircase output. So for the rising pulse, it is rising. It's represented by bit 1, and for the decline, it is represented by the 0. This is the decline. Decline is staircase, and the value is equal. Then the previous data is replicated. Okay, this is your delta. For the rising pulse is rising. For decline is 0, and then again just like this. So at each sampling time, the function moves up and down constant amount of the delta. Delta is the step size. This is the step size delta. Delta is the step size. The staircase function attempts to track the original waveform as closely as possible. This one, our main objective is to replicate this to in the staircase output. So at each sampling time, the analog input is compared to the most recent value of the approximated staircase function. Binary 1 is generated if the function is goes up, and binary 0 is generated otherwise. So for the rising pulse, binary 1 is generated, and for the decline pulse, binary 0 is generated. So this is a simple example. For example, this is your time axis. This is timely division, time division multiplexing, T0, T1, T2, T3, T4, T5, and so on. And this is your waveform. This is your analog signal, which is segmented into 6 parts. Six. The step size is this. This is the step size. For the rising, there is a one associated. Again rising, then one associated. Again rising, then one associated. Then decline, then zero associated. Then decline, then zero associated. Then rising, then one associated, and one associated. So when with the delta modulation, instead of transmitting a coded illusion of the simple sample, solely one bit is transmitted that merely indicate whether or not the sample is larger or smaller than the previous sample. It is the best type of the simplest type of the differential pulse code modulation scheme. Differential delta modulation signal is smaller than the pulse code modulation scheme. So modulation demodulation. So these are the modulator and demodulator circuit. The analog signal is fed into a summer, which is followed by the quantizer and integrator. Integrator is a device that integrates the input to the output. For example, if we give a square wave to the integrator, the output is a triangular wave. Uh, because the square wave on for the constant value either 0 or 1, the integration is the integrator is the output. Okay. So the delta modulation uses the oversampling technique to achieve the high signal to noise ratio. In delta modulation scheme, the transmitter circuit is composed of summer, quantizer, accumulator, and encoder interconnected with each other. This here the integrator circuit contain a delay of Ps. Delay can be provided using the integrator. The output of the integrator is a staircase approximately delayed by the Ps. The output of the integrator is the staircase. Okay. The staircase approximation is compared with the present and sample value at the summer, and the difference is given at the error signal. And at the receiver and the demodulator is just opposite to the modulator circuit. The error signal is given to the quantizer circuit, which consists of the hard limiter with the input and the output relationship. Here the error is quantized into two values, that is plus minus delta. Delta is the step size. Then the output of the quantizer is coded to produce the desired data wave. At the receiver end, demodulation is done using the integrated and low pass filter. The modulated wave is first decoded using a decoder. Then the staircase approximation is reconstructed by passing the positive and the negative pulses produced by the decoder and to the integrator. The outband quantization noise and the high frequency is taken away removed by passing the signal through a low pass filter whose bandwidth is equal to the original signal bandwidth. So there are two main modulation parameters for in case of your delta modulation, that is step size and the sampling time. So the step size should not be too small or not be too large. What happens is step size is small step size and Signal changes very rapidly. For a small step, the signal changes very rapidly, so it's underestimation. And for the larger delta, the signal changes very slowly. It's overestimation is only. And with respect to the time smaller t increases the overall accuracy. As the t is increases, the more and more information of this analog signal is valid, so it increases the overall accuracy. But smaller t increases the output data rate, that is the bps, but bits per second is increases because the bandwidth requirement is high. If we decrease this t, so delta modulation rule is smaller the delta, smaller the t, and larger the delta, larger the t. So this is the our this waveform I showed earlier, that is t0, and this t and this step size are equal. This axis is step size, this is the time division axis. So rising pulse is given the 1 and the declining pulse is given as a 0. So if we increase the step size reduced to 50% and the t is same, this step size is reduced to 50%, means we have shrunk this y-axis, but the t is the same. So what is happening now, we have a more number of the information. This is rising, 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 then decline, then rising, rising, rising. Okay, this is how we get this. Now in the next example, we have reduced both the delta and the time by the 50%, so we have a more number of the information is increased as the t size is increased. So this is how we get the waveform. For the rising, we get a positive, and for decline, we get a negative. For rising and decline, we get a. This is how we get the output waveform for the delta modulation system. So what are the advantage of the delta modulation signal? So some of the advantage are mentioned here. It was found that the lower bitrate delta modulation is better than the standard PCM. In delta modulation scheme, operating on the voice signal under the optimum condition, the SNR is increased by 9 dB by doubling the bit rate. Next is the increase in the SNR with bit rate is much more dramatic for the pulse code modulation than the delta modulation. Therefore, the modulation is recommended only in certain special circumstances, such as the when it is necessary to reduce the bit rate below the 40 kilobyte per second and the limited voice quality is tolerable. Next is the modulation method is used if the extreme circuit simplicity it is more simpler than the pulse code modulation overriding more than the accompanying use of high bit rate is acceptable. Next is the delta modulation works with the lower channel bandwidth. That is all that was I be told. It uses a time division multiple access. So the bandwidth requirement is low because in PCM we have to send the 3 bits, whereas in the this delta modulation we have to send only single bit. So the system makes it cost effective and simpler to implement. The feedback mechanism present in the modulation scheme ensure the quick and the robust delivery of the data. So what are the applications of the this delta modulation? Some of the applications are voice transmission systems such as telephone or radio communication highly prefer this modulation technique because the bandwidth requirement is very low. The delta modulation is mostly useful in the system where the timely data delivery at the receiver is more important than the data quality. The modulation is applied to the ECG waveform for the database detection and the real-time signal processing. For analog to PCM encoding and this modulation scheme is used, the delta modulation is applied in the television system. So what are the main difference between the delta modulation and pulse code modulation? In pulse code modulation, it stands for pulse code modulation, DM stands for delta modulation. In PCM, feedback does not exist in the transmitter or the receiver, while in DM, the feedback is exists in the form of the disintegrated. The per sample 14, 4, 8, and 16 bits are used. Here only 1 bit is used. The PCM requires higher transmission bandwidth, DM requires lower transmission bandwidth. PCM is a complex in terms of complexity and implementation, while DM is much easier to implement. So PCM has a good signal to noise ratio, while DM has a poor signal to noise ratio because loss of the information. PCM is costly, DM is cheap because of low hardware requirement. PCM may be a technique honed to digitally represent the sample and analog signal, digital to analog signal to digital converter. In PCM, signal requires an encoder and decoder both sides. In DM, signal can be modulated and demodulated. PM is mostly used in the video telephony and audio telephony, and delta modulation is mostly used in the species as well as the imaging. So that's about that we have discussed it. Thank you for your session. Thank you guys.